merci. Premièrement, Bernard, merci beaucoup pour cette invitation formidable et pour la visite à Paris. Très, très sympa. Okay. Mais pour la bonne santé de tous les gens dans cette salle, je vais continuer en anglais. It's wonderful to be in Paris. Coming from New York, especially, there is sibling cities, New York and Paris. So I love New York, but when I come to Paris, I embrace it. And it's wonderful to be here. So can we dim the lights a little bit? Just so it's a little easier to see the slide. Perfect. Very good. So will do my best to follow up on Bernard's lecture this morning. And the title of the talk is Within and Beyond the Realm of KPZ. So it will mainly be within the realm of KPZ. The work that I'll be talking about is primarily done with a colleague in the Netherlands, George Palazzanzas, Kazuma Takuchi in Tokyo, and then a young student who is now a graduate student at Harvard, Yusha Lin. Anyhow, much of what I have to say today can be found in a small review article in Journal of Statistical Physics that was published a few years ago. The focus of the lecture will be mainly on the universal qualities. My talk will essentially be croissance, désordre, but pas du tout de l'exclusion. Okay? I'm focusing on kinetic roughening, non-equilibrium stochastic growth, and les polymères dirigés, okay, that Bernard had mentioned earlier. So that's my bread and butter, okay, the directed polymer problem. So I show you here a picture. Bernard mentioned these bacterial growth problems. So here it is in a flat geometry. We've taken actually an experiment. I'm a theorist, but with students at Barnard at Columbia, we did some small experiments. You take a thread and you put it in bacterial broth, and then you stretch that thread in a petri dish. So this is nutrient-rich. There's lots of food in the agar. So very quickly, okay, over hours, the bacterial colony will grow this way, but also this way. I just show you the top half. And one is interested in the frontière, okay, the interface, all right, of this growing bacterial colony and how it gets roughened with time. So this is a problem of far from equilibrium. And as Bernard had discussed earlier in his lecture, we're interested in the variance, okay, of this interface, the speed at which it moves, the vitesse, but also the largeur, the width of the interface. Now, I need to stress that this is basically a reaction-limited process. It grows quickly because the nutrient agar is very rich in nutrients. You could imagine doing an experiment in which the agar is very nutrient poor, so that the growth is diffusion limited, the DLA that Bernard mentioned earlier. So in that case, you would get a very different bacterial colony growth. It's a fractal object of great geometric complexity. Now, I like to begin this talk with the comparison of the two because both of these problems are very rich and produced much research. But there's a danger with this one, all right? This is a very intractable problem. It's a very dangerous problem for students to study because it's hard to make progress. Whereas this problem of the KPZ is a very rich problem as well, but has tractable elements. So you can get your teeth into it. You can make progress and then see the new challenges. So anyway, let me just talk briefly about the DLA, because for me, it's a cautionary tale in a way. So I show you a simulation of a DLA cluster. So we had inoculated at the center of the petri dish, so to speak, And in this computer model, you have food particles basically wandering in and sticking, okay, and allowing the bacterial colony to grow. Because the growth is fractal, it gives rise to these branches, and the branches don't allow particles to penetrate deep into the DLA cluster. So at the end of the day, you have, as I said, an object that is quite complex. It's a fractal object. It's a stochastically created object. If I were to run a different simulation, I would get a different shaped cluster. But there are certain universal properties of this DLA cluster. So for example, the main benefit, so I stop the simulation and I show you the largest DLA cluster of the 1980s. So we said at the time it was the Guinness Book of World Records, the gold medalist, okay? 10 million particles. The different colors have to do with, you know, the time at which the particles were released. So it's clear that the computer model does something correct in actually capturing the fractalness of the actual bacterial colony that is grown under starvation conditions. If you do lots of numerical experiments, you discover that the DLA cluster, when it is embedded in 2 dimensions, has a fractal dimension of about 1.71, plus or minus 0.01. If you do many biology experiments, you discover, in fact, that the fractal dimension of that bacterial colony is close to 1.71. So the numerical simulation, the model, is doing a good job of capturing the fractal dimension of this cluster, but it's very hard to do anything theoretically, all right, beyond that. You cannot predict the fractal dimension, all right, of the DLA cluster. So the model was actually created by Witten and Sander in 1981, and this is some more than 35 years ago now. And, well, in classical mythology, in the epics of Homer and Virgil, it is said that the face of Helen launched 10,000 ships. This paper launched, well, not 10,000 papers, but many, many papers. It was a tremendous inspiration. But as I had indicated earlier, this problem of DLA is rich, it's quite seductive, but very difficult. So what we're going to do in this talk is to, instead of starving the bacterial colonies, we give them nutrient-rich food. And we will focus on the situation where the growth is actually reaction-limited rather than diffusion-limited. So that is the realm of KPZ, okay, focusing on that kinetically roughened interface, the frontière, okay, the boundary, and as it propagates up. So quickly, the outline of the talk, I will focus mainly, initially, on the 1+1 case, KPZ, and then I'll talk about the polymère dirigé. Bernard covered a lot of ground this morning. He talked about the exponents, beta, chi, and also z. And then he also broached the subject of the universal limit distributions, the Tracy-Whittem distributions from random matrix theory. So a few years ago, there was a KPZ workshop in Kyoto. And at that point, I likened the situation of 1+1 dimensions to the Golden Temple in Kyoto. It's elegant. It is refined. It's, at this point in time, the theory for KPZ in 1+1 dimensions is very refined, very advanced mathematically. It was the province of physicists for 25 years, but then the mathematicians caught a hold of it. And they proved rigorously, okay, these Tracy-Whittem distributions and the connection to the KPZ problem in 1+1 dimensions. Now, 2+1 is a rather different story. If I stick with the Japanese culture, okay, if 1+1 KPZ is like the refined Golden Temple, then in a quite different product of Japanese culture, 2+1 dimensions, okay, is much less refined. it's all developing, okay, in a kind of in a busy fashion right now. There are lots of outstanding problems. Most of the work in 2+1, all right, has been done numerically. So I will discuss that in the second half of the talk. All right. But much like Godzilla and also Ghidra, okay, the three-headed monster, this is a kind of mashup situation, okay? It's ripe for doing things, okay, because things have been disrupted and people are looking for answers. Finally, I'll conclude. I see that there are some students here. I will conclude with some open problems. But just keep in mind that a lot of this material has been nicely covered in a special issue, okay, devoted to KPZ in the Journal of Statistical Physics, okay, of 2015, which Herbert Spoon, okay, has edited with Joe Leibowitz. So Bernard mentioned Spoon many times in his talk. He's a senior statesman and has done many, many things over the 30 years of KPZ. Okay, so let's go to the beginning. Okay, let's talk about 1+1 KPZ. So what do we have in the beginning? Well, in the beginning, of course, we have Carter, Parisi, and Zhang. Okay, they have the creators, okay, of the KPZ equation, which I'll be focusing on through much of my lecture. Meron Carter is a professor at MIT. Giorgio, of course, famous Italian physicist. And Zhang was a postdoc of Parisi in Rome, but is now in Fribourg, Switzerland. Now, of course, the KPZ equation is, for me, the beginning. But we know all beginnings tend not to come from vacuum. There has to be something present that helped that beginning. And so you can see over the right shoulder of God, there are three cherubim. And they are Van Beijeren, Kuttner, and Spoon. So there was a physical review letter the year before KPZ, which was quite critical to the birth of the KPZ equation. A few years before that, there was a very important paper due to Foster, Stephen, and Nelson, okay, are here below God. All right, but in the beginning, for our purposes today, we don't have to worry so much, but of course, it was built upon previous work, these two very important papers. So the focus is on KPZ today. And as Bernard mentioned earlier, okay, the starting point here is a physical review letter that dates to 1986. It has not launched 10,000 ships either, but it has also inspired many, many papers. It's not quite, well, the DLA paper is about 5 years earlier. It has more citations, but this is a paper which in America we say is legend. Okay, it is a legend. Bernard wrote down the equation, all right? The KPZ equation is meant to be a continuum description of these kinetically roughened interfaces. As he pointed out, okay, on the left-hand side, there's basically, well, h is the height of the interface. Or it's always the height. So this is h dot, okay, so that's the velocity on the left-hand side, the velocity of the interface, or the time derivative of the height. There are three terms in the KPZ equation that basically interact and give rise to the interesting scaling behaviors. There is a Laplacian term, which if you take in isolation, it's just the heat or diffusion equation. It's relaxation. The solution is a Gaussian. Okay. But the KPZ equation has this characteristic nonlinearity. So this is 19th century physics. Heat, it's Fourier, diffusion, all right? But then we add in, okay, a nonlinearity, which goes like the square of the gradient. And then finally, noise. So having an equation with the Laplacian and noise is a Langevin equation. So this is 100 years ago. But what makes this problem particularly interesting and particularly rich is the presence of this nonlinear term. So you have relaxation, you have the nonlinear growth term, and you have stochastic noise. Now, we usually assume that the stochastic noise is uncorrelated, all right, spatially uncorrelated, and temporally uncorrelated. And the strength of the noise, the bruit, okay, is given by the parameter d. So this equation has three parameters: nu, which sets the strength of the relaxation; lambda, which sets the strength of the nonlinearity; and then finally d, which sets the strength of the noise. Now, as I mentioned a moment ago, recently the mathematicians have gotten a hold of this equation, and in particular, Martin Harrer, who was a 2014 Fields medalist, for his work on stochastic partial differential equations. Okay? That work, which led to his Fields medal, was essentially tied to a very long and complex paper that he wrote about the KPZ equation and other stochastic PDEs. So I can't stress enough, and Bernard has already indicated, that this whole KPZ revolution has moved from the court of the physicists partially into the court of the mathematicians. And there's always an interesting synergy when you have mathematicians and physicists working together. Okay, so quickly, Bernard had mentioned some models, okay, ballistic deposition, which is basically a toy model of thin film growth, or molecular beam epitaxy. The younger people in the audience probably recognize it as a variant of a computer game called Tetris, okay, perhaps. But as I stressed, okay, our interest is in this rough edge. So this is actually a ballistic deposition simulation. Bernard mentioned Eden growth, so up there we have Eden growth. And then finally, the RSOS model. So what is the key point? The key point is that these three different models have different stochastic growth rules. For ballistic deposition, it's vertical drop and stick upon first contact. In the Eden clusters, which are meant to be a toy model of bacterial colony growth, you're basically, the rule, the microscopic local rule, is that all perimeter sites are equally likely. And then finally, here with RSOS, the solid-on-solid model, okay, with the restriction that height differences between neighboring columns cannot be larger than 1. Okay, so here you can see that the possible growth sites are indicated by the red dots. I cannot add a particle on top of the mountain here, because then the height difference would be 2. That's a violation of the local rule. Anyway, so these are three different growth models. And if you study the width of the interface, you discover, I think Bernard showed this in his handout, that the width of the interface as a function of time, so this is just the most naive thing. You calculate the mean position of the interface, and then the variance about that mean position. You take the square root, that is the width. So there is a characteristic exponent beta, which captures the kinetic roughening with time of these stochastic growth models. So the three different curves correspond to ballistic deposition on the top, Eden growth in the middle, and then RSOS on the bottom. This is a double log plot. So when you expect a power law, you always make a double log plot, because the slope in the double log plot will give you the exponent. So in this case, if you were to take out a ruler, calculate the rise over the run, you would find that the exponent beta is essentially a third. All right. Now, you can do this kind of simulation for many, many models. There's a huge universality class, polynuclear growth, which will be important for later. Gates-Westcott, anisotropic ballistic deposition, the single-state model. There are dozens of models that all exhibit this scaling with beta equal to 1/3 in 1 + 1 dimension. So this is the early time roughness. So they constitute a very large universality class. All right? Again, my interest is in the universal properties of roughening, and KPZ universality class is the most significant one for us today. As Bernard had indicated in his lecture, so I don't need to spend much time on this, there is a scaling ansatz for the width. So if you do a simulation, of course, you do a simulation on a computer. So the system size L is finite. So maybe it's 100. All right, and then maybe you increase it to 200 and then to 400. If you study the width as a function of time, it saturates eventually at some L-dependent value. So there is an exponent key, right, which dictates how the saturation width of the interface scales with the system size L. He also mentioned that there is a scaling ansatz for the width. It's a function of t and L, two variables. But there is the very special combination of t over L to the z, which basically introduces this dynamic exponent, z. So it looks as if I have three exponents, but in fact, there's a relationship between the dynamic exponent z and chi, which is the saturation width exponent, and the early time roughness exponent beta. So not three exponents, we're down to two. All right, so here's the KPZ equation. And the question is, does it capture the universality of these discrete microscopic growth models? The answer, of course, is yes. Okay? There are very sophisticated tools, among them the dynamic renormalization group, which is basically perturbative in the nonlinearity lambda, but using a field theoretic technique, you go to one loop, you go to two loop, you follow the flow, the renormalization group flows of these parameters, nu, d, and lambda, all right, which I had indicated here in the KPZ equation. Remember, nu is the surface relaxation parameter, lambda is the nonlinearity, and d is the stochastic noise. So anyway, using field theoretic techniques, you can study renormalization group behavior of the system, and then because of a symmetry of the model, there is this KPZ exponent identity, which Bernard had indicated. The exponent chi, and the saturation with exponent chi, and the dynamic exponent z always sum to 2, all right, for all dimensions. In 1 + 1 dimensions, there's the fixed point is retrievable. There's a Fokker-Planck approach, which basically pins down chi is a half, z is 3/2, and beta is 1/3. Bernard has already motivated that in his talk. So the thing that you need to remember in 1 + 1 is that these exponents are all known, all right? It's basically 1, 2, 3, all right? So chi is 1/2, all right, beta is 1/3, and then z is 3/2. And chi plus z is obviously summing to 2. So this is a fairly sophisticated renormalization group approach, but other methods have been used to attack the problem, even in 1 + 1. Okay, so at this point, if I'm teaching a student about this, I'm trying to convince them that the KPZ equation has something to do with Eden clusters and ballistic deposition and restricted solid-on-solid model. They know nothing about dynamic renormalization group. The students are young, so the most sensible thing to do is to just give them the KPZ equation and have them numerically integrate it. You just numerically integrate the stochastic PDE. You study the fluctuations, okay, of the height of the interface. You average over many realizations, okay, of the stochastic noise. And you look at the roughness of this variable h. And what you discover numerically, when you look at this equation on the computer, if you look at the width as a function of time in a double log plot, not surprisingly, but a bit of a surprise for the student, you see that the exponent beta is very close to 1/3, 0.32. So this doesn't take a lot of work, okay? The first time I did this with a student, her name was Bonnie Taminga, and she did not know a lot about computers. I taught her a little bit of Fortran, and this was the plot that she produced, okay, in her junior year at Barnard College when she was 19 years old. But anyway, she's now a full professor at Yale, but she studies neutrinos, not KPZ problems. But I thought it was a good beginning for her anyhow. So the point is you can numerically integrate this equation, and I will do this in higher dimensions later. to extract the scaling exponents and the distributions, okay, associated with the roughness of the interface. Okay. So I'm actually showing you not bacterial colony, because that would be too slow. I'm showing you a fire line. So you take a piece of paper, you put special chemicals in it so that when you ignite the paper, it doesn't flame up, because you don't want flame. You just want a flameless fire line. So you put a wire along the bottom of this piece of paper, and then you run a large current through the wire. The wire ignites a fire line. The fire line consumes the paper. So these combustion fronts are actually in the KPZ universality class. All right, so I show you here. Okay, there's the signature of the artist. Okay, this is Junzang. So he's the younger brother of Yicheng Zhang of the KPZ equation. He's a professor at Rockefeller, but in his youth, in 1992, he did the very first fire line experiment. It was fairly crude, but it was very provocative. It was a wonderful experiment done with great skill. In the years that followed Zhang's first experiment, there was a Finnish group that really got into it. They loved this experiment. So they very carefully spent many years, okay, studying the kinetic roughening of the combustion of paper. So here are some of the interfaces up top, all right? Here's a digitization of one of those interfaces in a snapshot. But the basic point is that they can study the roughness of these flameless fire lines. They can extract exponents like beta, which they confirm 1/3. These are difficult experiments, but the evidence is quite strong in total. They also extract, using the correlation function, the width exponent chi equals 1/2, okay? So the ratio, again, of chi to beta gives you z, which is the dynamic roughening exponents. So there were later papers. So this physical review letter dates to 1997, just 5 years after the first paper of Junzang. But then in the years that followed, they refined, okay, these flameless Finnish fire lines, okay, became all the rage. And the folks in the KPZ community were always looking, okay, forward to the next paper by the Finnish group when they were producing these fire lines. Okay, so there's much more to this problem than just the second moment, which is the width of the interface. One wants to understand the full probability distribution of the height fluctuations. So obviously, if you're doing an RSOS experiment or numerical experiment, or you're simulating an Eden cluster on a computer or a ballistic deposition, you can study the entire spectrum of the height fluctuations, the full probability distribution. So that was done, okay, and shown here for the RSOS kinetic roughening, so 1 + 1 dimensions. And in 15 minutes, okay, on, you know, a MacBook Pro, you can basically make a picture of the probability distribution of the height fluctuations, where you have subtracted the mean and divided by the variance. Okay, so it's 0 mean, unit variance. But as Bernard pointed out, this is not a Gaussian distribution. That is perhaps the most important message of the talk. This is an asymmetric distribution. And the tails, okay, are certainly not Gaussian. All right? One tail has an exponent which is 3/2. The other tail has an exponent which is 3. So they're not 2 on either side. Now, the key thing is that, of course, this asymmetric distribution has a non-vanishing skewness, which is something a little bit more than 1/4. It's negative. It also has a non-vanishing kurtosis. So the skewness involves the third moment. The kurtosis is the fourth moment. And these height distributions have a universal skewness and a universal kurtosis. So these are key numbers in 1 + 1 KPZ. They characterize this all-important asymmetric probability distribution for the height fluctuations. So I'm showing you in the large figure the RSOS model, but in the smaller figure, upper left, it's actually the height fluctuations of the KPZ equation itself. So the same student, Bonnie, that I had simulate and study the width of the interface, I could have the same program and look at the full height fluctuations. And when you do that for the KPZ equation itself, you get the red curve. And this red curve could be placed directly on top of the black curve. So it shows that the probability distribution for the full probability distribution for the height fluctuations is universal, or at least I'm showing that it's the same for the KPZ equation and the RSOS model. If you measure the skewness for the KPZ equation in this very modest simulation, very modest, it's giving us 0.276 as compared to the 0.29 for RSOS. The kurtosis, which is related to the fourth moment, is 0.15, and here 0.17. But these are very modest simulations that a high school student can do at this point. Okay, so now I shift gears pretty quickly. I would like to talk now about the directed polymers, which is the flip side of the coin for me. Okay, so this is, I talked about croissance. Now I will discuss Désordre, okay, these polymers Derrida. And so we're starting fresh now, a new topic. Okay, so if I lost you in the first part, uninteresting, now this is a new start. So I consider a very simple problem. Let me remind you of a problem that you already know. Suppose I start at the origin. Forget about the numbers on the plot up high. Suppose I just flip a coin. If I flip a coin, it comes up heads, I go diagonally to the right. If it comes up tails, I go diagonally to the left. Heads, heads, tails, tails, heads, so on. If I average over many coin tosses, and I ask, well, what is the average X position for the coin flipping random walker? Obviously, it will be 0 because of symmetry on the left and on the right. If I asked about the wandering away from that symmetry axis, we all know, Brownian motion, that the RMS displacement goes like the square root of the number of steps, the square root of time. So that wandering exponent is 1/2, always 1/2 for a coin flipping random walker, for Brownian motion. It's just the diffusion equation, okay? One time derivative, two space derivatives, I'm going to get x goes like the square root of t, just by dimensional analysis. This is a very simple problem. It's independent of numbers of dimensions. You can have in 1 + 1, 2 + 1, 3 + 1, the exponent is always 1/2. The probability distribution is always Gaussian. It's a beautiful problem. But a much richer problem is a directed random walk in a random energy landscape. So now I'm not flipping a coin. Flipping coins is all about entropy. What I'm doing is I'm putting on my bonds in the lattice random numbers, let's say random integers between 0 and 9. And then I'm looking at the paths that go, okay, through that random energy landscape. And the energy of each path is the sum of the energies of the bonds that are visited along the way. So if you look quickly along the right diagonal, this costs a lot of energy. Okay, 8, 4, 6, 9, 1, okay, along the right diagonal, 1, 7, 4, 9, 4 along the left diagonal. If I'm looking to minimize the energy, then the side diagonals of the wedge are not going to be very likely. There are many more paths that are near the middle. Anyway, I've indicated in green the globally optimal path after 5 steps. Okay, it's 1, 2, 1, 0, 1, so that's just 5 units. It is the lowest energy path through this random energy landscape. So the time direction is up, the x direction is transverse, and I'm interested in the fluctuation in x as a function of time. But this problem has not only fluctuations in position, it also has fluctuations in energy. Because if I look at a different realization of the random energy landscape, and then the path up to the 5th time slice will very likely have an energy it'll be in a different position, of course, with high probability, but it will also have a different energy. So in this directed polymer problem, which goes back to Hughes and Henley, 1985, and Meron-Carter, 1985, there are actually the two fluctuating variables, position and time. If you look at the entire collection of locally optimal paths, you get an interesting ensemble here that might have something to do with, in 3 dimensions, let's say, optimal networks, like capillary networks in the eye, for example. OK, so suppose I go now to the computer. I look at these directed paths in a random energy landscape, and I study the fluctuations in the position, x, and in the energy, OK, delta E. So E is energy, x is position. There will be an exponent called zeta, which is the wandering exponent. And there is an energy fluctuation exponent, which I call omega. And what one discovers, again, in a very modest computer simulation, maybe steps that are, walks that are 1,000 steps long, that if you average, the RMS fluctuation in the position, it scales as the 2/3 power. Again, this is a double log plot. Okay, double log plot gives me the exponent as the slope. It's pretty noisy, but it's a very modest simulation. I see that the wandering in this random energy landscape is actually super diffusive. It is larger than 1/2. Remember, coin flipping random walker, that's entropic wandering. That's normal diffusion, where the wandering exponent would be 1/2. In this problem, which is an optimization problem, there are certain times when it's quite advantageous to wander well away from the central axis. So what one discovers, at least numerically, is that the wandering is super diffusive, and the exponent is larger than 1/2, in fact, quite close to 2/3 numerically. The fluctuations of the energy of the globally optimal path actually scale with a power which is close to 1/3. So this directed polymer problem has 2 exponents, zeta and omega. And one can show, not surprisingly, I mentioned that these are flip sides of the coin, that the problem of directed polymers is intimately related, okay, to the problem of stochastic growth. All right. So the way to understand this is to look at the partition function for the directed polymer. And here I've made a little sketch imagining that there are 2 transverse dimensions, x1 and x2, and then there is always the longitudinal direction where the walk is directed along, and that's called the time axis. So these directed polymers are a toy model, if you will, of a vortex line, okay, an elastic object in a dirty superconductor, for example, where in the partition function, you have to sum over all paths, okay, at the top here, and you're summing over all paths of the Boltzmann weight, and the energy is basically given by a competition between elasticity, which wants the vortex line to be straight, and a random pinning potential. All right, that's a function of x and t. Now, in the simplest scenario, the random pinning potential is uncorrelated and Gaussian. All right, so there's delta function correlation in space, delta function correlation in time. Now, if you just do a simple scaling analysis and you look at the first term in the Boltzmann factor up there, it's basically 2 powers of x. You see the dx dt squared. So I essentially have 2 powers of x, and then I have 2 powers of time in the derivative, but then I have the integration element, which is a dt. So that first term is essentially 2 powers of x over 1 power of time. Since the x, okay, since x scales like t to the zeta, and the energy scales like t to the omega, then if I put those 2 things together, okay, I discover that basically the energy goes like, which is the energy fluctuation, goes like t to the omega, but the x squared gives me a 2 zeta, and the t in the denominator gives me 1 less power of time. So there must be a relationship between the exponents omega and zeta. And of course, we see that it's true, at least in this case, numerically, highly suggestive. Omega, 1/3 is twice zeta. Twice zeta would be 4/3 minus 1, which is the 1/3. Okay. So in fact, the connection is, well, the deep connection has to do with the fact that one can take that partition function, which is basically a Feynman path integral. In your quantum mechanics, you learn that there is the standard formulation due to Schrödinger, which is a differential equation, but then there's also the path integral formulation, where you're summing over all paths. If we go from the Feynman path integral representation, which is this partition function up here, to the Schrödinger formulation, if we just simply substitute in, for example, well, we get this differential equation, which is a Schrödinger equation. Here's the kinetic energy term, but then here's the potential energy term. So this is a Schrödinger equation for a particle in a dynamically random pinning potential. If I make a substitution for the free energy rather than for the partition function, what I discover upon substituting this into that equation is that the free energy of the directed polymer actually obeys the KPZ equation. So this is the link. This is the important connection between these two problems. So the point is that the free energy of the directed polymer is analogous to the height in the stochastic growth problem. So they're both governed by the same exponent, the 1/3. So the early time roughness in the KPZ problem is analogous to the energy fluctuation exponent in the directed polymer problem. If you remember when I introduced the dynamic exponent, it connected a time with L to the Z. So basically, it turns out that if you want to connect a length to a time, well, that's the correlation length, okay, that Bernard mentioned earlier. The correlation length scales like T to the 1/Z. All right? So the relationship for the positional fluctuations, okay, that wandering exponent, okay, in the directed polymer problems, zeta, is equal to 1 over the dynamic exponent in the KPZ problem. So in the KPZ problem, in 1 + 1, that exponent was 3/2. So 1/3 is the 2/3 that we were seeing right here. All right. Okay. So you might ask, are there experiments, okay? Are there experiments in which people have measured the wandering exponent of directed polymers? And in fact, there has been an experiment, okay, in 1 + 1 dimensions. And in that experiment, one basically considers a piece of paper, and one tears that piece of paper. But one does it very carefully. Okay? You can't just tear a piece of paper in half. It has to be done in a reproducible fashion. It also has to be done very carefully. You can't, if you pull on it, then there's a kind of instability which ripples it in the cross-section. So what one has to do is to wrap the paper around a pipe on the top, wrap the paper around a pipe on the bottom, and pull the pipes apart. So there's a very slow, okay, quasi-static process whereby, well, what is paper? Paper is a random medium. It's made of fibers, and the linkages of those fibers have random energies. So you might imagine that if you tore the piece of paper slowly enough, okay, that the tear line would go through the minimal energy path. And in fact, while the Finns were burning paper, the Hungarians were tearing paper and doing very careful. There was a paper institute, okay, someplace in Hungary where they were able to get many different kinds of paper. Yeah, the Institute for Paper Research in Hungary. They looked at papers of many different densities and thicknesses and different materials. But basically, the point was to understand the roughness or the wandering of this fractal tear line. So the main point is that it is not a random walk. It's nowhere near a random walk. The exponent that characterizes the roughness of this tear line is not 1/2. In fact, in the experiment, so here's a digitization of the fractal tear line. They do a scaling analysis, double log plot, and they basically extract an exponent which is 0.67 plus or minus 0.05. So one can argue about the precision of the experiment, but the main takeaway message certainly is that it is not a random walk. Okay, it's most likely something which involved optimization of the path. Experts can argue that it's more related to directed percolation, but for our purposes today, it's a very provocative experiment which suggests that these fractal tear lines are essentially realizations of the directed polymer in 1+1 dimensions. Okay. All right, so let me go back now to the probability distributions. I showed you this distribution before. I showed you for restricted solid on solid model. But now I can do simulations of the directed polymer, these optimal paths through a random energy landscape. I can study the energy fluctuations, because the analog of the energy in the directed polymer problem, okay, the energy in the directed polymer problem is the height in the KPZ problem. So what you always do in these simulations, you subtract the mean, divide by the standard deviation. So that's the variable A that I showed you in the previous plot. Same thing here, except what I'm now superimposing is the RSOS probability distribution and the directed polymer. So I want to convince you that beyond the exponents, in fact, the full probability distribution, the directed polymer problem and the KPZ problem are, in fact, identical. But I had already convinced you, I hope, by the little mathematical transformation and the Schrodinger equation and so on. All right, so let's look at this probability distribution a little bit more carefully. And as Bernard had mentioned, it's not Gaussian. The tails, okay, have characteristic exponents, which, in fact, from KPZ scaling theory, you can relate the exponent of the left tail, the longer tail, to the exponent omega, or the exponent beta. So in fact, you can show that eta, the tail exponent here on the left side, is 1 over 1 minus omega. Omega is 1/3, so you basically get a tail exponent of 3/2. The tail on the right-hand side was shown by Dotsenko to have an exponent of 3. So the left-hand side is 3/2, the right-hand side is 3, definitely not Gaussian, but this figure shows you the universality of this distribution. So this figure was in fact published in a paper by Kim, Bray, and Moore in 1991. All right? So it's a very powerful paper which establishes the universality of KPZ and the directed polymer problem at the level of the probability distribution function. All right, so now I fast forward to the year 2000. Bernard mentioned there was a very famous paper by Prohofer and Spoon. Okay, there's Herbert Spoon on the right. And the important point about this paper, it started a second KPZ revolution now. So 15 years after the introduction of the equation, they established that the probability distribution that I just showed you right here, all right, was in fact, so this is now a log, semi-log plot, so you're seeing the tails, was in fact related to the Tracy-Whittem distributions in the random matrix problem. So you're looking for the largest eigenvalue of the random matrix, the statistics of that largest eigenvalue, depending upon whether it's a Gaussian unitary ensemble or Gaussian orthogonal ensemble. These correspond to, as Bernard pointed out, different initial conditions. So a radial geometry, all right, which he was emphasizing, is the Gaussian unitary ensemble, and the flat interface is the Gaussian orthogonal ensemble. But the key point about this paper is that basically studying, they showed that the polynuclear growth model is related to the very famous problem of the statistics of the longest increasing subsequence in a random permutation. This is the Ulam problem. But then in 2002, okay, well, actually 2000, Andrei Okunkov, okay, showed that the problem of the statistics of the longest increasing subsequence of a random permutation is exactly the same as the statistics of the random matrix problem. This was a highly non-trivial paper which basically won him the Fields Medal in 2002. So this is a very interesting intersection point. I think Bernard will talk in the coming weeks a little bit about the random permutation problem. And certainly, actually next week, Satya Majumdar will be telling you folks about the random permutation problem in more detail. So I won't spend that much more time on it. The key point is that there are 3 different distributions. 2 of them correspond to the different initial conditions, and then the third one corresponds to the stationary state fluctuations. But as I had mentioned earlier, these Tracy-Whittem distributions, at least for the flat initial condition, has a characteristic skewness well known of 0.2935, and that's the same number that I had gotten for the KPZ equation and for the RSOS model. Okay, so there was continuing work on the flameless Finnish fire lines. They actually were able to show, okay, in a fairly crude experiment, that the full probability distribution of the height, the fluctuations in these flameless fire lines, essentially are modeled by the Tracy-Whittem distribution. Okay. But the real tour de force experimentally occurred in 2010. So this is now the 3rd KPZ revolution. Okay, the decade from 2000 to 2010 was somewhat productive, but not super productive. But then in 2010, in the experiments that Bernard had mentioned, Kazumasa Takuchi, using these turbulent liquid crystals, was able to realize at a very high level of precision the Tracy-Whittem distributions in this KPZ system for both flat and radial initial conditions. He was also able to study in great detail, as Bernard had mentioned, the important feature of the KPZ problem, that the velocity of the interface is a function of time. It only asymptotically approaches, okay, its asymptotic value, and there's a finite time correction, which is t to the minus 2/3. Okay. So all of this came together with some important theoretical papers. The year 2010 saw the exact solution of the KPZ equation. There were 4 distinct groups who solved, okay, the exact solution for the KPZ equation in 1 + 1 dimensions. There were 2 groups of physicists. I don't know how this is possible. They were a kilometer or 2 apart, but they did not discuss the problem with each other. They solved it independently. I think this is the shortest possible distance, which is possible to do things independently, and then publish, okay, one paper on top of the other paper. They must have seen each other in a cafe or a bar or something, but somehow, from outside appearances, Viktor Dotsenko, okay, solved, this is his EPL, his Europhysics letter, and then also Pierre Le Desalle, Alberto Rosso with their Italian collaborator Calabresi. In order to, they solved the directed polymer problem in 1 + 1 dimensions. You have to go beyond the ground state in the replicated Hamiltonian. You have to include all the excited states. There's a clever trick involving an area integral. But at the end of the day, they were able to show that in the directed polymer context, these Tracy-Whittem distributions emerge. So there were 2 French groups, okay, Dotsenko at power 6, and then Pierre at the École Normale, who, working on the directed polymer in a physics kind of calculation, solved the KPZ equation in 1 dimension. Then there was also a 3rd group, Sasamoto and Spoon. Their paper was more mathematical physics. It was a little bit more rigorous, but the 4th group, which was associated with Ivan Corwin, is a rigorous mathematics, all right? So this made the whole thing completely legitimate from a mathematical community point of view. So 4 different groups, the same year, 2010, solving independently the KPZ equation in 1 + 1 dimension, leading to a very complicated discussion involving Fredholm determinants, okay, to actually solve the equation. So the probability density for the height fluctuations is given by a Gumbel distribution convoluted with a Fredholm determinant. So it's a quite heavy affair, mathematically speaking, at least if you're going the whole 9 yards with the rigorous math. But these Fredholm determinants are actually quite useful. Most physicists don't have too much exposure to Fredholm determinants, but once you learn about them a bit, you're able to actually explore some interesting issues in the problem. And that includes, for example, understanding how the tail exponents emerge. So near the peak of the distribution, okay, so again, this is the height fluctuation as a function of the number of standard deviations. Near the the peak of the distribution, then effectively it's Gaussian, okay? It's just a Taylor expansion around the peak. So the effective exponent is around 2. But as you roll down this tail, okay, the exponent drops from 2 to 3/2 in a way that you can calculate with the Fredholm determinant. Going to the other tail from the peak, 2, the right tail, the exponent rises to the value 3, which Dotsenko had predicted, okay, a number of years earlier. So you have the 3/2 on the left tail, the 3 on the right tail, basically Gaussian in the middle. The Fredholm determinant gives you all the information that you need to sketch that out. Okay, so maybe time to move on to 2+1. So here, the situation is much more in play. There's much more work to be done. So I see a lot of young students out there, so I'm hoping to engage you in some of these and some of the, yeah, so anyhow, 2+1, I can do simulations in 2+1. For example, I can study various directed polymers in 2 transverse dimensions, 1 longitudinal dimension. In this particular plot, I have 4 different directed polymers. Sometimes the energies are Gaussian distributed on the sites or on the bonds. In other instances, there might be a uniform distribution of energies on the sites or bonds, or maybe an exponential distribution, like in yellow there, a distribution of energies on the bonds. I also look at the RSOS model in red, and then I also numerically integrate the KPZ equation. So I'm studying here now the universal probability distribution of the height fluctuations in 2+1 KPZ directed polymer. So one of the things you learn immediately is that, again, it's asymmetric. The skewness is larger as you increase the dimension. Okay, remember, it was 0.2935 in 1+1. It is now 0.2424. The kurtosis also grows as you go from 1+1 to 2+1 dimensions, 1652 here to 0.346 up there. There have been experiments, okay, looking at these 2+1 dimensional surfaces. There was a very well-known experiment by Dutch scientist here, Palazzansis, paper published in 2002. He was looking at the probability distribution of the height fluctuations in a 2-dimensional film. And basically looks like this, looking down. So there are valleys, there are mountains. One is interested in the roughness of this surface. The particles that are being dropped are not little squares, okay? They're actually sticks, okay? They're oligomer molecules that have this kind of chemical structure. So it's a little bit complicated because you're not just dropping cubes, okay, like you are in the numerical simulation. But anyway, when you study the probability distribution of the height fluctuations, you subtract the mean, you divide by the standard deviation, so it's a dimensionless variable. The experimental data is indicated in the orange dots. The black dashes are my integration of the KPZ equation. So the experiment is kind of challenging, but it turns out when you look at the semi-log plot, the experimental data points in this oligomer film, the kinetically roughened surface, fall pretty nicely onto the KPZ numerical curve. All right? So there, at the same time, well, not at the same time, there was a paper published by a Brazilian group which looked at cadmium telluride silicon semiconductor films. And again, there's basically a KPZ curve. This is their data points. And they extract skewness, which is quite close to the kurtosis. Well, the kurtosis is almost dead on. The skewness is a little bit off. But we're basically looking at 2-dimensional surfaces now. And you use Stanling STM to image those surfaces. All right. But these distributions are experimental ones are not universal. Okay, something that Bernard touched upon but requires great attention is you want to extract what is the universal limit distribution, all right, for the universality class. What I did initially here was to just subtract the mean and divide by the standard deviation. That's fine in a first pass. Each of these models, okay, has a different value of nu, a different value of d, a different value of lambda. And in order to extract the holy grail, if you will, the thing that's at the heart of the matter, one needs to come up with a way of expressing the probability distribution in terms of a dimensionless variable, which involves subtracting out the mean here and dividing by, as Bernard had indicated, the variance, okay, the square root of the variance. But each model has a different value of d, nu, and lambda. The d and the nu turn out to be essentially, it's the ratio of d to nu that's relevant. We call that a. And then, so at the end of the day, there are these parameters lambda and a, and a scaling variable, which is gamma, a to the 1 over chi times lambda. There's also the interface velocity v infinity. So if you know gamma and v infinity for each of the models, you can actually look at the height fluctuations, translate it into this fundamental variable, and then at least in 1 + 1, you would get the Tracy-Whittem distributions. So what I'm interested here is in the higher dimensional analogs of the Tracy-Whittem distributions. So I need to do the extra work. There's extra lifting to figure out what those model-dependent parameters are. So that's what I'm doing here in the 2 + 1 dimensional case. So the plot that I showed you a moment ago, there are 7 different models, 4 directed polymers, 2 growth models, and then the KPZ equation itself. So RSOS is one of the growth models, and I have 4 different directed polymers, and then I have the KPZ equation. So this was the simplest, the first pass, if you will, where I'm just subtracting out the mean and dividing by the standard deviation. But if I go back, and for each of the 7 models, I actually determine the KPZ nonlinearity. I determine the parameter A. A is the ratio of d to nu, all right? And I also determine the asymptotic growth velocity for the growth models, or the asymptotic free energy per unit length for the directed polymers. I have all the necessary parameters, because once I know lambda and I know A, and I know the saturation width exponent chi, then I can calculate the gamma, which I guess in this table I'm calling theta. But anyway, each model has its own value of lambda, its own value of A, and so its own value of theta. At the end of the day, my interest is in this dimensionless variable, h minus v infinity t divided by, well, gamma before, t to the beta. So in 2 + 1 dimensions, beta is not 1/3. Beta is a little bit larger than 0.24. Chi is not 1/2 in 2 + 1 dimensions. It's a little bit less than 2/5. All right? So these are the different values of that exponent chi for these 7 different models. Anyway, I'm just showing you here not all 7 models. I'm showing you in blue the directed polymer with Gaussian noise on the sites. In red triangles, I'm showing you the restricted solid-on-solid model. And black diamonds, okay, black diamonds for KPZ. So I've integrated the KPZ equation in 2 + 1 dimensions. And for each of these 3 different systems, okay, the directed polymer in blue, KPZ in black, and RSOS in red, I'm actually looking, okay, I'm slicing through the data, and with the known values of V infinity and theta for those 3 models, looking at the fluctuations in this quantity, all right? And that's giving me this universal distribution. So this is the analog of Tracy-Whittem in 2 + 1 dimensions. You might ask, how does one get the value of lambda for a model? How does one get the value of A for a model? It's not hard. You can show from the KPZ equation, it's all about the velocity.
Bernard already indicated that if you look at a system with a finite size L, then the velocity is not going to be, it won't achieve its asymptotic value. So there's basically a toolbox of techniques that go back to Joachim Krug and Paul Meekin, which I call the KM toolbox. If you put the system in a box of finite size L, then there's a correction to the asymptotic growth velocity, which goes like 1 over L to the power 2 minus 2 chi. In 1 plus 1 dimensions, chi is a half, so the 2 minus 2 chi would give you 1. So there would be a finite size correction to the growth velocity in 1 plus 1 that goes like 1 over L. In 2 plus 1 dimensions, chi is not a half. It's a little bit less than 2/5. But anyway, we can estimate its value. But the prefactor there in equation A involves the product of A times lambda. The other trick, okay, in the toolbox is that if you grow the surface not flat but tilted at some slope s, then there's going to be a correction to the growth velocity, which goes like s squared. And the prefactor there is lambda. So that, in fact, that's what I'm showing you in figure B here. For the RSOS model, as I tilt the surface, okay, then the growth is reduced. If I tilt the surface or the substrate, then there are more sites that are, you can't grow them, the solid at that site, because the slope is increasing it. So anyway, the tilt-dependent growth velocity allows you to extract lambda by equation B. And from the tilt-dependent growth velocity, I get lambda. And then from A, I can get A. So that's how I get lambda and A. Then I get theta. And then I'm able to actually plot the universal limit distribution, which is the 2 plus 1 analog of KPZ. Sorry, of the Tracy-Whittem distributions. So again, these are numerically the universal limit distributions that are the higher dimensional analog of Tracy-Whittem. All right. Correlators. Well, you can also look at spatial correlations, okay, between 2 points. Equal time, but spatially separated points. So this is not a 1-point function, it's a 2-point function. And it has to do with the separation R between the points. So numerically, and also looking at the polymers and the growth models, it's possible to come up with a universal covariance, okay, of these, the height correlator. And that's basically if you scale, okay, the separation between the points R by an appropriate power of t to the 2 beta, you scale the correlator by a similar power, you can get the different models to collapse upon a single universal curve, which is indicated by the orange dashes here. If you take the experiment, you can actually use this universal covariance for the spatial correlator to extract the value of lambda for the experimental system that I showed you back here. Okay, so I can go back to this experiment. I can look at the statistics of the height fluctuations, look at the correlator in the system, and then basically pull out a value of lambda for that experimental system. So for the experts, it's clear that this is pretty non-trivial to be able to do that, because I'm not tilting the surface in the experiment. But by the correlator, I can actually, this is the first known instance in which the KPZ nonlinearity has been extracted by the scaling analysis. Okay, so I have a few more minutes, I think. Yeah? So I've kind of covered the situation, since the KPZ renaissance in 2010. The experiments of Kazumasa Takuchi, and then the tour de force theoretical calculations of the 4 groups, which gave us an exact solution of 1 plus 1. So I want to finish now, as I said, since there are students in the audience, okay, with some open problems. So these are what I would refer to as challenge problems. And so let me just spend maybe 5 minutes on each. The first one actually goes back to a beautiful paper that Bernard wrote, okay, in the late 80s. And I was a young student, and I got very inspired by it. So everything that I have talked about so far has been on Euclidean lattice, okay. But you can create other lattices, one of which is called a hierarchical lattice. And it's a kind of iterative structure in which you start with a bond, but then you replace the bond by this gnomon, okay? So it's basically B branches. There are B branches, and each consisting of 2 segments. So then at the next step, each branch here gets replaced by this thing, and so on. So at each iteration, you're doubling the length. I'm going to be looking at a directed polymer on these hierarchical lattices going from this point to this point. But as time goes on, the surrogate for time here is the iteration of this hierarchical lattice, which at each step doubles the length of the system and introduces more and more branches, okay, within the branches. So anyhow, this is a well-known alternative lattice. It often has some interesting analytical possibilities. And in this case, what's special about it is that you can actually derive a recursion relation which connects the probability distribution of the fluctuations of the energy of the polymers on this, well, I call it a diamond lattice. Okay, so this problem for me, this challenge problem is diamonds in the rough. So the point is to actually solve the recursion relation for the probability distribution. So this would be the analog of Tracy-Whittem distribution, but for this very special hierarchical lattice, which has this B as a parameter in the problem. So B is kind of a stand-in for dimension. You can show that the effective dimension of these hierarchical lattices is 1 plus log B base 2. And in the limit that B is very, very large, okay, then you're basically, it's an optimization problem, and you're just looking for the extremal path, which is essentially given by Gumbel's statistics. So here I'm showing you the log of the probability distribution as a function of the scaled variable. I'm subtracting the mean, dividing by the standard deviation. So there are 2 interesting limiting cases. B equal infinity corresponds to a Gumbel distribution. Okay, I know the answer is Gumbel distribution if B is infinity. If B is equal to 1, then basically I just have a branch, and I'm just doing a convolution of the energies of this branch as I double the length of it, so I know that that's going to be Gaussian. All right, so in between B equal 1, which is known exact, and B equal infinity, which is known exact, in between Gauss and Gumbel, there's no exact solution for this fixed point probability distribution. So the challenge in this problem, and then what Bernard did originally, was to actually calculate the energy fluctuation exponent as a function of B. Okay, here it's been laid out a little bit more. But increasing B is like increasing dimension. And the idea is that this omega, which is like the beta, omega-directed polymer is like beta KPZ, basically falls with increasing B. But the challenge is to actually solve the recursion relation for the limit distribution. So I put that out there. There are many important features that the directed polymer on a hierarchical lattice shares, okay, qualitatively with the directed polymer problem on Euclidean lattices. So this is challenge problem number 1, diamonds in the rough. Challenge problem number 2, well, I mentioned to you that the exponents in 2 plus 1 are not known. So the exponent beta is definitely less than a quarter. So 1 plus 1, it's 1/3. All right? In 2 plus 1, it's close to 0.241. All right? So the best work to date is by Kelling and Odor. And here is the effective exponent beta in 2 plus 1. They're dropping octahedra in this growth model. It's 2 plus 1. It's ballistic deposition, basically, but with octahedra. And as t goes to infinity, the effective exponent comes in at about 0.242, 0.241. Okay, but a quarter is up there. Why do I mention a quarter? Because back in the day, 1989, Jinmin Kim and Mike Kostelitz, this is Mike Kostelitz who won Nobel Prize for something different in 2016, but he was involved in this whole KPZ enterprise early on. They wrote a very provocative paper in which they proposed that the dimension dependence of beta was 1 over d plus 1. So in 1 plus 1 dimensions, d is 2, 2 plus 1 is 3, you get beta equal 1/3. So that's what you see here, beta equal to 1/3. They did simulations of the RSOS model and d equal 3, and they saw what they thought was a quarter. In 3 plus 1, they thought they saw 1/5. In 5 plus 1, they thought they saw 1/6. So these are pretty old simulations. It's quite clear that Kim Kosterlitz's conjecture is probably wrong. Numerically, okay, the experiments are putting it closer to 0.2415. So the point is to actually try and calculate exactly what beta is, find the exact value. If you don't like beta, you could look at chi, or alpha. So that's the saturation width exponent. So here, the critical paper in recent years is due to Pagnani and Parisi. And they basically estimate chi in 2 plus 1 dimensions. Again, less than 2/5. They're finding 0.3869. All right, so Geza, Odor, and Kelling are finding a little bit larger than 0.39. In the paper that I wrote with the 7 models, I'm finding chi a little bit less than 0.39. So I have a wager out with Giorgio Parisi about whether it's less than 0.39 or more than 0.39. So I have my money on the number less than 0.39. And things are looking good for me right now. So anyway, getting an exact value is going to be very hard. So for the mathematicians in the audience, maybe there's a way of conjuring up a bound, okay, on the exponent. So I've talked about beta, I've talked about alpha, and then there's also z. Z is the dynamic exponent. And basically, z is chi over beta. So the chi is like 0.39, and the beta is 0.2415. So remember, from the family Vichek scaling ansatz, the ratio of chi to beta would give you z. And in 2 plus 1, the ratio of those two best numbers is giving you 1.615. 1.615 is tantalizingly close to the golden ratio. .618. So in the third digit, past the decimal point. Anyway, it keeps me awake at night. I wonder, will somebody be able to show it's a golden ratio? In fact, the golden ratio came up in a very amusing paper by Gunther Schutz and his colleagues that was published in PNAS, Proceedings of National Academy of Sciences, in which they discuss the Fibonacci family of dynamical universality classes, of which KPZ is one. Here's the Fibonacci sequence. Here's the 3 halves in 1 plus 1. So we'll see. OK, so I've talked about KPZ in 1 dimension. I've talked about KPZ in 2 plus 1 dimensions. What about KPZ in a dimension between 1 and 2? Suppose you looked at a KPZ kinetic roughening or directed polymer on a Sierpinski gasket. What you discover in that case, interestingly, if you measure the Sierpinski gasket has a fractal dimension of log 3 over log 2. It's 1.585. If you measure the early time roughness exponent, you get something like 0.27. That's not 1/3. You get an alpha, which is like 0.48, which is not 1/2. Okay? And then z, which is alpha over beta, the ratio of those numbers is 1.78. So remember the fundamental identity of KPZ, alpha plus z is 2. Well, when you add alpha and z here, you don't get 2. All right? So this is definitely not KPZ, or it's a different kind of KPZ. In fact, the number that you get is essentially the 1 over the random walk exponent on that Sierpinski gasket. Anyway, for those of you who like to look at different dimensions, okay, or fractional dimensions, this is a curious place. There have been some nice papers written about that recently. Okay, so I finish up now with the last problem. And the last problem, I actually gave a talk like this 2 years ago in Santa Barbara. And with each of these 3 problems, okay, I confessed that they were very difficult problems. So each of these problems came with a bottle of whiskey, Lagavulin. So I promised at that point, anybody, and this is still a promise that I will keep. If you solve one of these challenge problems, you will be well known, but you will also get a bottle of Lagavulin, Scotch whiskey, from me. Because these are important problems. These are problems that keep me awake at night. So there was an extra credit problem, okay, in Santa Barbara 2 years ago. And this had to do with the Fraunhofer-Spoon paper. There were 3 universal distributions in 1+1 dimensions. And this was the flat case. This was the radial case. And then there's the stationary case, the stationary statistics. So if you actually study the crossover between the flat case and the stationary statistics, what you discover when you look at the skewness is that there is a non-monotonic behavior between the Tracy-Whittem value, which is the 0.2935, and the stationary case, which is known as Bach range, which is 0.359. So there's a funny dip in the skewness, okay, as you look at the crossover between flat and stationary statistics. In fact, this little dip has been seen in Takeuchi's experiments, and the universality of it has been verified by looking at other models, like the stochastic heat equation and RSOS and the polymers. So I put this out there as a challenge problem, and as it turns out, a local fellow, okay, Pierre Ledussal, working with Takeuchi, they saw a non-monotonic behavior not in the transition or the crossover from flat to stationary, but they saw a non-monoticity in the crossover between the radial geometry, okay, and the stationary statistics. So they were going not from here to here, but from here to here, so radial to stationary rather than flat to stationary. And it turns out when they look in the experiments, so it appears not in the skewness, but in the variance. It's very subtle. So this is the variance as you go from the radial case to the stationary case. And this is the asymptotic value. So the curve will reach its asymptotic value, then reach some minimum, and then rise. So the challenge problem involved the crossover from flat to stationary, and it had to be done analytically. So Pierre, in a 70-page paper that was published in JSTAT, so this is following a March 2017 paper where they did it numerically. But anyway, in a 70-page paper, Pierre was able to show analytically, as I crossed from Bach range to the radial distribution, that there is in fact a Takeuchi minimum in the variance, okay, not in the skewness. So in the radial to stationary crossover, it's in the variance. So he wasn't tired enough with the 70-page paper. There's an additional feature which happens in the crossover from radial to stationary. The temporal correlator actually does not go to 0, but approaches an asymptotic value, which Pierre, in a 50-page paper that was published just last month, he calculated to be 0.623. So I had done a simulation, the paper is in December, but I had done a simulation 1 year ago in January, and I had studied this so-called weak ergodicity breaking in the radial to stationary crossover, and my numerical simulations had calculated that universal quantity to be 0.626 with an uncertainty of 3 in the last digit. So in his abstract, he quotes the value 0.623, and that 0.623 is very close to where I'm getting the 0.626. So although Pierre has analytically calculated it for the radial to stationary case rather than the flat to the stationary case, between the 70-page paper and then the 50-page supplement for the PRE, I thought that the problem has been solved from my perspective. So I will be going at some point this afternoon and delivering a bottle of Lagavulin Scottish whiskey to Pierre. And in fact, Pierre, I think, is giving the final lecture in this series. So another possibility is that I could perhaps leave it with Bernard. Is it okay? You won't open it? Or you can open it when he comes. Okay, maybe I pass it over to you then for now. So anyhow, there are 3 outstanding problems, and I can promise you I am good for the bottle of whiskey. I will FedEx it to your door if you solve one of those 3 problems. Je reste ici. Merci beaucoup.